Hello friends, I am Dr. Ankit Jain and I welcome you in our YouTube channel SOMAS Evaluation Classes. As we know, high performance liquid chromatography is an analytical technique to separate, identify and quantify components in a mixture. It is the single biggest chromatographic technique essential to most laboratories worldwide. In this video, I will explain the various analytical parameters which we kept in consideration while interpreting HPLC chromatogram and how these parameters affect the accuracy of analytical method. So chromatogram is a visible or pictorial record showing the result of separating the component of a mixture by chromatography. It is a plot of the detector's signal as function of elution time or volume. Chromatogram should be checked to ensure the chromatographic quality including good peak shape, baseline drift, column bleed, sample carryover and chromatographic resolution are within acceptable limits. In a chromatogram, for qualitative assessment of compound, we used to observe retention time, where for quantitative estimation of analyte, we record the peak area of particular analyte. Now, various chromatographic parameters are assessed from chromatogram to characterize the peak, to identify the column effectiveness, and to define the suitability of the system with the analytical method. These chromatographic parameters are retention time and volume, void time and volume, column efficiency, retention factor, selectivity or separation factor, resolution between peaks, tailing and asymmetric factor. Now we will be studying the way to characterize the peak in a HPLC chromatogram. First of all, a major quality parameter of chromatogram, that is retention time. So retention time is the represented by TR in the figure, is the time elapsed between sample introduction and the maximum signal of the given compound at the detector. Also you can say it is the time elapsed between sample injection and 50% elution of the component. It is the time that a solute spent in a column, or it can be defined as the time spent in the stationary and mobile phase. The longer retention time depends on the interaction of the analyte with the stationary phase. The stronger the interaction, the more will be the interaction time. Now retention volume. It is the volume of mobile phase needed to move a solute from its point of injection to the detector. It is represented by VR. Dividing the retention volume by the flow rate of the mobile phase, we can easily predict the retention time of analyte. Next is void time and volume. Beside the solute peak, figure also shows a small peak at time interval of Tm, which eluted soon after the sample of injected into the mobile phase. This peak is nominated as unretained peak. So void time is the time for elution of an unretained peak in a chromatogram. However, volume of the mobile phase consumed up to appearance of unretained peak is known as void volume. Void volume, also known as interstitial volume and represented by V naught or Vm, refer to the total volume of mobile phase in the column, the remaining space in the column being occupied by packing material. In porous material, it includes the interstitial and intra-particle volume. The volume can be determined by injecting an unretained substance into the column, which measures the void volume plus the extra column volume. Then moving toward the column effectiveness parameter. First among them is column efficiency. It is used to compare the performance of different columns. It is probably the most frequently cited parameter of column performance and is expressed as the theoretical plate number. Efficiency can be changed by altering the column length, particle size or flow rate of the chromatographic system. The higher the number of theoretical plates in a column, the higher the efficiency of it, and after that the more resolution can achieve. And for measuring the column efficiency, we employing the equations given in the video, that is n equal to 16 whole square of tr by width at base. In this equation, W represents the width of the eluted peak and subscripts B and 0.5 represent the height of the peak at the base or at 50% respectively. For an optimum HPLC analytical procedure, the N should be more than 2000. Next is the retention factor, formally referred to as a capacity factor and represented by character K prime. The retention factor measures the period of time that the sample component resides in a stationary phase relative to the time it resides in mobile phase. It is calculated from the ratio of adjusted retention time by the time. For an unretained peak, adjusted retention time means retention time after subtraction of the void time. The third factor to evaluate the column effectiveness is selectivity or separation factor. The separation factor is a measure of the time or distance between the maxima of two peaks, represented by alpha, and if alpha is equal to 1, the two peaks have the same retention time and co-eluted. Selectivity can be changed by changing the mobile phase constituents and changing the stationary phase. Temperature may also be a factor in adjusting selectivity. Now let me tell you about the chromatographic parameters which are responsible for system suitability. First among them is resolution, represented by symbol RS. Resolution describes the ability of a column to separate the peaks of an interest, and so higher the resolution, the easier it is to achieve baseline separation between two peaks. Resolution takes into consideration efficiency, selectivity, and retention. To completely separate two molecules, RS must equal to or more than at least 2. The equation for evaluating the resolution is given in the video. Other factor for establishing the stability of a system is related to peak shape, and that is tailing or asymmetric factor. If the peak to be quantified is asymmetric, a calculation of the asymmetric would also be useful in controlling or characterizing the chromatographic system. Peak symmetry arises from a number of factors. The increase in peak symmetry is responsible for a decrease in chromatographic resolution and precision. Tailing factor, represented by B and measured at 10% peak height, is distance from the point at the peak midpoint to the tailing edge. A is the distance from the leading edge of a peak to the midpoint of the peak. As in the video, asymmetric factor is computed by the ratio of B to A. If the magnitude of asymmetric factor is more than 2, then it is not acceptable for a suitable HPLC analysis. For an ideal or perfect peak shape, the asymmetric factor should be 1. If it is more than or less than 1, then the peak is not symmetric. The reason must be tailing or fronting in the peak. That was all a brief account chromatographic parameters. If you enjoyed this video, please do like and subscribe our channel Mass Evaluation Classes, and for more interesting videos, stay tuned with our channel. Thank you.